Hi there, I'm going to talk about lipids in this section, in this lecture today. And lipids are just a fancy name for fats and oils. We need those in our body to do a multitude of functions, so they're very important in our body. And we also eat them. We eat fats and oils, and we need some of them are called essential fatty acids because we cannot produce those in our body. So we do need to eat fat and oil in our daily diet so that we can be healthy and produce the things that we need in our body. So there's two types of lipids. Lipids are big molecules, and they're insoluble in water. That means they're non-polar, but they can be dissolved in organic solvents because they're mainly formed from carbon and hydrogen. They have some extra things like oxygen and other elements in them, but mainly the bulk of them, the majority of the molecule is carbon and hydrogen. So we divide these lipids into two classes. One is the simple lipids, and these are very important biomolecules in our body. They're steroids, which are formed and make up our cholesterol that we need for transport of things in our body. They're also for our sex hormones, estrogen and progesterone, testosterone, are steroids, and then there's also other steroids. So we'll talk about those in this lecture. There's also simple lipids called prostaglandins, which are used in your body when we have fever and pain. And then there are also simple lipids called leukotrienes, which are important molecules for allergic and inflammation responses in our body. So those are the simple lipids. And then the complex lipids are the Triacil Glycerols, fats and oils that we use in our body. And then we also have special complex lipids that are parts of our cell membranes called Phospholipids and Sphingolipids. So here's an example of fatty acids. Fatty acids can be straight or they can be curved. And so if the molecule has no double bonds at all in it, it's called saturated. That means there's the most possible hydrogens in the molecule. That's called saturated. So they're long chains of carboxylic acids. They have a polar end. That red dot you see is polar, and it's the carboxylic acid end, and then the rest of the molecule is long. It can be 10 to 24 carbon atoms in the carbon chain, and remember, carbon and hydrogen together are non-polar. They do not dissolve in water. So one end of the molecule is polar, can associate with water and likes water, and then most of the molecule does not like water. It's really important to help fatty acids make structures in our body, knowing that one end likes water and one end does not like water. So saturated fatty acids are completely filled up with hydrogens. There's no double bonds in them. And so because they're nice and straight like that, they can lay flat against each other. They stack well. And so these types of fatty acids are going to be solids at room temperature. So if you eat, if you've ever seen lard or butter, things like that, they're solids at room temperature, so they're saturated. And then unsaturated things have one or more double bonds in them. And because as soon as you put a double bond in there, it twists the molecule a little bit. And then those chains are not straight anymore, and they cannot lay flat. And so anything that has unsaturated fatty acids in it will be an oil, because those molecules cannot lay flat, and they're going to be liquids at room temperatures. So we kind of talk about these fatty acids with this numbering system. You see it on the left there. It's the number of carbon atoms in the whole molecule, and then how many double bonds are in that molecule. So the fatty acid that comes from palm trees is called palmitic acid. It has 16 carbons in it, and there's no double bonds anywhere. Then things like linoleic acid has 18 carbon atoms in a chain, and it has 2 double bonds. You can see those double bonds in the middle here. 1, 2, linoleic acid. And so that makes that chain twist and turn, so it's not going to be flat. So saturated molecules are going to lay flat. They have a carboxylic acid end here, but the rest of this is going to lay nice and flat. So these are going to be solids at room temperature. Then the unsaturated ones are going to be oils at room temperature. So these fatty acids, remember, they're long chains, but they have that carboxylic acid end. So it depends, if they're at low pH, they're going to be in the acid form. So they're going to have the Cu ending, C double bond OH, carboxylic acid ending. They're going to have this H attached. If the pH becomes more basic, they're going to disassociate that H plus and the C double bond O negative. So that's going to dissociate at higher pHs. When it looks like this, it's going to be nice and water soluble. This is going to be polar, and this is going to be even more polar and wanting to be able to dissolve in water. So, like I said, when they lay flat, they stay at they're solids at room temperature, so they have a higher melting point than these twisted ones, the unsaturated ones, because these are oils at room temperature. These that are straight saturated are laying flat, and they're solids at room temperature. So here's some melting points. You see that the saturated ones have higher melting points. That means they're solids at room temperature. These have lower melting points. They're liquids at room temperature. So these molecules, these fatty acids, can do chemical reactions. So if you look at the side of some bad snack foods, you'll see a lot of hydrogenated fats. You'll see the word hydrogenated or hydrogenated. So that's here, like if you compare natural peanut butter to the normal kind of peanut butter, you see the grocery shelves, the Jif and the Skippy and stuff like that. They've hydrogenated that peanut butter, the oil in it, so that it will be solid at room temperature. So what they've done is they've added hydrogen atoms to this double bond, and they've removed that double bond and turned it into a single bond. So they've saturated it. So that's called hydrogenation, and you'll see that in a lot of bad snack foods. People are thinking that maybe this is not so good for you to eat as a lot of saturated fatty acids, and that the more natural peanut butter that's liquidy that you have to stir up together might be better for you. The other thing you can do is you can add water across that double bond. We saw that when we talked about alkenes and alkynes. You can add water. You can split this water into 2 pieces and add one side to this carbon, one side to that carbon. Remember, the action always happens at the double bond. So we can hydrate this molecule and turn it into something with OH on one carbon and H on the other. It follows the Markovnikov rule. We can also add halogens to that double bond. So X is saying a halogen. And we use this reaction to actually test fatty acids to see how much saturation they have. So the more halogen we could add to a particular sample means that there's more double bonds in the fatty acid. So that's a test. It's called the iodine test. So let's talk about Triacil Glycerols, and you'll hear the word triglycerides. These are non-polar complex lipids, and they're used for energy reserves in our bodies. Fats from animals are solid at room temperature, and oils from plants are liquids at room temperature. It has a glycerol shape here, 3 carbons in a row with OHs on it. And then this molecule reacts with long chains and forms these long complex molecules. So like we said, oils are liquids at room temperature because they have a lot of double bonds in them. And so here's that glycerol backbone, and then we've added these long chains to that backbone. And like I said, we could do that iodine test to it. We can add iodine to see how many double bonds are in a molecule. And so that's a test that people do in the food labs to see how many double bonds are in a particular fat or oil. So we can also oxidize these fats and oils. When we do that, it causes a rancid taste. If you've ever eaten something that's really old, you'll taste that bad taste for that the oil or fat's gotten bad. You'll see it when you can open up a bottle of really old oil, and you can see that it's kind of cloudy, and then it smells weird. That's called rancidity. And so what's happening is oxygen is actually breaking those double bonds and making the fats and oils go down to smaller pieces, and it doesn't smell good to us. We actually smell the carboxylic acids and the aldehydes in our noses, and we don't like that smell, and we know that the oil and fat has gone bad. Another reaction is a saponification, where we can take fats and oils and we can add sodium hydroxide to it and form it into soaps. So that's how soaps are formed. So these are why we need to have all these fats and oils in our body. We use fats and oils and store them so that we have energy reserves. If we face a starvation situation, animals use it to keep them warm. Fats and oils have more energy per gram. So fats and oils contain 9 calories per gram of energy, and carbs and proteins have 4. So from a energy standpoint, it's better to eat fats and oils if you need calories. Most of us in America don't need that extra calories, but that's why they're important. Especially like when there's a program in poor countries where kids are starving, and they'll give them concentrated fats like peanut butter to keep them from starving, because there's so much energy in fats and oils. So some of these fats and fatty acids are building blocks for our molecules, and some of the fatty acids we must consume in our diet because our body can't produce them. That's called linoleic, and linoleic acids are essential fatty acids. We must consume them. So complex lipids are used in our membranes. So all our cell membranes are made of a very complicated structure of fats, and phospholipids are the most common membrane lipids. So we use something called phospholipids. That's a fat that has phosphorus in it, and the most abundant phospholipid that we use in our body is lecithin. And there's also some that are used in other areas of our body called the sphingolipids. So phospholipids have a fatty acids end. It has a glycerol in the middle. And it has a phosphate group on one end, and then it can also have some other things as well on the end. But the main thing to look at for us is fatty acid, the glycerol, and a phosphate. So that's where the phospho part comes, and this is the lipid side, the fatty acid and glycerol together. So there's many different kinds of these phospholipids, and we draw them when we're just talking about them in general with this hydrocarbon tail, and then the polar end that can be soluble in water. So these are really, really important when we talk about cell membranes. We have the hydrocarbon nonpolar side, and then we have the polar water-loving side of these long molecules. And this is important to form cell membranes. Here's some more. Here's are the sphingolipids. They have a polar side. The red part is more polar, and then the black and white is the carbon-hydrogen bond, their nonpolar end. So there's a polar end and a nonpolar end. There's lots of different things that can be added to each end, but they generally have this structure where one side's polar and one side's nonpolar. So let's talk about the simple lipids. These are they don't have that fatty acid linked by ester bond, that glycerol with the 3 tails on it. These have different structures. So the 3 that we're going to talk about here are steroids, prostaglandins, and leukotrienes. So simple lipids that are steroids have this ring structure. So look for this if you need to find out if it's a steroid. It's got these 3 hexagons, and then it's got this pentagon here. That's the steroid nucleus. Very important molecules in our body. And they have, this is the basic structure, the steroid nucleus, and then there can be other things attached to it. But look for this to classify something as a steroid. And we use steroids in our body to form sex hormones. Our body produces these from cholesterol that is in the body. And you'll notice that these are found, like here's an estrogen, progesterone. These are more found in higher percentage in a female body. This testosterone's higher percentage in a male body. And if you notice, they're very, very similar. So that's why I think it's fascinating that just a small change in these molecules can produce such a change in our bodies. It's very interesting. But look for this. You're looking for this 3 hexagons and a pentagon shape to say that that's a steroid shape. And here's some more that you might have heard of. Prednisone, cortisone, these are used when people have, sometimes are used in therapies when people have arthritis or some other autoimmune disease. So those are important molecules you might hear of when you get into health careers. So steroids are important in our digestion. One type of steroid is bile salts, and the cool thing about it is it has a polar side and it has a non-polar side. And so what it's able to do is when you eat a lot of fats in your diet, it goes into your stomach and then into your small intestine, and then your liver produces bile salts. And the bile salts go into the intestine, and they start breaking these big giant chunks of fat in your intestine into smaller pieces. They do something called emulsify. They surround the molecule so that these ends are water soluble, and the nonpolar side of these bile salts surround the nonpolar fat molecule. And then these little droplets can be transported in your body. and more easily digested. So they make this big giant chunk into smaller chunks that have a higher surface area, and then your body can deal with them better and use the energy from that fat that you've eaten. Some other ones that we need to talk about are prostaglandins, and these are important molecules that work in the role of helping us when we have fever and pain. And then leukotrienes are generated for allergic and inflammation responses. So these beautiful fatty acids and fats and these molecules that we talked about can form something called micelles. We kind of saw how the polar side and the nonpolar side orient themselves in the environment that they're in when we talked about the bile salts. So, for example, if these little molecules are in water, they're going to orient their polar side towards the water side of the environment, and then their little hydrophobic tails are going to all come together, and they're going to stay close together. And so our body uses this micelle type of thing, and I think some drugs and people are inventing use this structure to deliver drugs to the body. And other things that can happen are we can have these polar ends of those phospholipids form towards the water side of the environment they're in the body. And then these nonpolars can orient themselves like this and turn into bilayers. And we can even have something more complex where we have this kind of bilayer system turn into a ring here. And we can have water on the inside, no water here, this hydrophobic, and then have water on the outside. And this is also a mechanism that we can introduce medications to a patient by putting the medication on the inside of this little ring and then having the person take the medication, and then it's goes to the body where it's needed. One of the last things we're going to talk about is the fluid mosaic model of membranes. And so, as you can see, we've got the little hydrophilic, the water-loving ends of these phospholipids oriented as a bilayer. We've got the polar lipids here, and then their hydrophobic ends oriented towards each other. So this is what we believe the cell membrane looks like. We've got this long layer, and it surrounds the membrane of the cell or other areas of the body. And inside this membrane, we've got proteins that are doing important work. We've got cholesterol molecules. These can keep this structure more pliable and fluid so that things can move around. So that's what the cholesterol is doing in this cell membrane. We can also have these little things called glycolipids. They've got glyco means it's got sugar, and lipid means fat. So this is a combination of sugar and fat. Some of these are like little flags on your cells to tell other cells what type of cell it is. So it's like little flags identifying the cell. So there's lots of different little molecules in these cell membranes that do a lot of work. We need to get some things into the cell, and so there's different ways that can happen. Sometimes simple diffusion can happen. Diffusion is a natural process where areas of high concentration and low concentration, nature's not happy with that. So it'll try to equilibrate and make the concentration the same on both sides. So really small atoms, ions, molecules can do simple diffusion through the cell membrane and try to make the concentration of these red molecules the same on the outside, end on the inside. That's called simple diffusion. But bigger molecules can't do that. And some parts of our cell membrane have pores in them, which are just mean holes. This is a protein channel formed by proteins, and it's got a little hole in it, and it allows for some molecules to get through that are the right shape and type to go through this cell membrane. That's called facilitated diffusion. And then the last type of diffusion is called, sorry, oops, I went the wrong way. Go backwards. The last type of transport is active transport, and this is where actually we have these proteins in the cell membrane, but this proteins actually have to use energy, cellular energy, to make a molecule from the outside move into the inside, or from the inside move to the outside. That's called active transport. Active because this protein needs energy for this to happen. It's not just a hole in the cell membrane. It's actually like a little pump where the protein actually pumps molecules from one side to the other. So that's called active transport. We also have lipoproteins in the blood, and these are called complexes of lipids and proteins. The name lipo is the fat part, and protein is the protein part of these complicated molecules. And these lipoproteins transport lipids in the blood, and you've heard about these. You've heard of cholesterol in your blood. There's low-density lipoproteins that transport cholesterol from the liver to the cells of the body. And then we have high-density lipoproteins, HDLs, that transport cholesterol from the body cells back to the liver. And then, you probably know when you get a blood test that they compare the LDL level to the HDL level to see if that's a good ratio. And if you have a high ratio of LDL to HDL, that's been correlated to cardiovascular disease like heart attack or stroke. And LDL is sometimes referred to as bad cholesterol, and HDL is sometimes good. And so, your blood work, frequently they look at your lipoproteins to see what that ratio of LDLs is to HDLs. And that's it for this lipoprotein lipids lecture. And the most important part in this lecture is, I would say, the cell membranes, knowing that transport across the cell membrane, the model of the cell membrane and what's part of that cell membrane. So those are really important. And then being able to look at a molecule and see if it is a steroid or not, and understanding the structures and the physical properties like melting points, oils or liquids, and fats are solid at room temperatures. Those are all important to know for this section. Thanks so much for listening. I'll talk to you soon. Bye-bye.